Okay, so text-to-video AI, it's moving incredibly fast, right?
Yeah.
But the really cutting-edge stuff now, it's not just about making it look real.
No, it's about adding that fourth dimension,
Yeah.
almost. Transparency.
Exactly. The alpha channel. We're
Yeah.
talking RGBA video generation, that's RGB color, plus that crucial alpha layer for transparency.
Yeah, and this is a really valuable visual format. I mean, if you've ever used custom emojis or maybe designed graphics for games or done professional video editing,
Oh yeah, needing assets you can just drop onto any background.
exactly. You definitely understand why high-quality RGBA video is so sought after.
But the technical challenge there is just huge, isn't it?
It really is.
Yeah.
Compared to plain RGB video or images, getting large amounts of good RGBA data, especially video data with motion, it's way, way harder.
Yeah.
Much scarcer.
And that scarcity makes training these big generative models super challenging.
Right. And, the previous attempts like the Model Transpixeler, which was kind of the state of the art before, they really struggled.
How so? What was their approach?
Well, they tried managing the alpha channel by, like, duplicating parts of the network architecture and adding special tokens. It got complicated.
Which sounds computationally expensive.
It was. It essentially doubled the inference cost, the time it takes to generate something. And honestly, the visual quality often wasn't quite there either. Kind of a brute force method.
Okay, so that brings us to Wan-Alpha. This is a new framework, and the claim is it learns both RGB and alpha together, but does it better.
That's the idea. Better quality, better transparency, and crucially, much, much more efficient.
Right. So our mission for this deep dive is to really get into the weeds, academically speaking, look at the specific techniques, the architectural choices Wan-Alpha uses to pull this off, where others, well, didn't quite hit the mark.
Exactly. We need to look at how they're encoding transparency efficiently and how they're guiding that whole learning process with a lot more precision.
Okay, let's unpack this. Starting at the beginning, the variational autoencoder, the VAE, that's kind of the foundation here, right? People tried this for images first.
That's right. The first real step was layer diffuse. They showed you could train a VAE to sort of embed RGBA image transparency into the standard RGB latent space.
But that took a ton of data initially.
1 million images, yeah. Although later work, like Alpha VE, showed you could get that number down significantly, maybe to around 8,000 samples, which is more manageable.
Okay, but moving from static images to video adds that whole motion complexity. You can't just use an image VAE directly.
No, you really can't. You lose temporal consistency. Things start looking jittery or inconsistent frame to frame if the model isn't built for video.
Right, and as you said, the earlier video models tried duplicating the architecture, so what was Wan-Alpha's insight?
Their core idea was, look, we don't need to double the whole network. We just need a smarter way to compress all 4 channels, R, G, B, and A, into that same latent space used by the RGB model. Efficiency was key.
So they trained their own VAE, called Wan VAE. How does it manage to merge 4 channels of data without, making the computation explode?
Well, they were smart about it.
Yeah.
They used a pre-trained VAE for the RGB part, so they leveraged existing knowledge. Then they focused on integrating the alpha channel.
How did they integrate it?
They actually duplicate the single alpha channel 3 times, just to match the dimensions of the RGB channels. Then both the encoded RGB stream and this prepared alpha stream get fed into a special component.
Which they call the feature merge block.
Exactly. The feature merge block, that's where the magic, so to speak, happens.
Okay, so physically merging the information, how does this block combine them without doubling the heavy lifting computationally?
Right. So this block takes the encoded features from RGB and alpha and combines them to predict that single merged latent representation, Z. And the crucial technical choice inside this block is their use of causal 3D convolution modules.
Causal 3D convolution. Why that specific type? What's the advantage over standard 3D convolution?
Okay, so standard 3D convolution can be really computationally heavy, especially if you have long video sequences. And sometimes it looks at information kind of all at once, future and past, which can mess with the sequential flow.
Oh, okay.
Causal 3D convolution, on the other hand, is generally cheaper computationally. But more importantly, it enforces causality. The calculation for any frame only uses information from previous frames, never future ones.
Which sounds critical for video.
Absolutely critical. It helps the model maintain much stronger temporal coherence, that smooth motion flow, which is non-negotiable if you want realistic-looking video.
Okay, that makes sense. Now, shifting gears a bit, but staying with the VAE training. This is where it gets maybe even more academically interesting. Training an RGB VAE is tough because the model can confuse background color with transparency.
Yes, that's a fundamental challenge. If the model sees, say, a black pixel, is that a black object? Or is it a clear object over a black background? The VAE needs help figuring that out.
So how does Wan-Alpha provide that help?
They guide the VAE learning using two specialized rendering functions during training. They call them hard render, or $3, and soft render, 3.
Okay, let's take the hard render $3. What's its specific job?
The hard render is designed to force the VAE to focus only on learning the true RGB color of the foreground object. It does this by taking the alpha channel and basically making everything that isn't fully transparent completely opaque, setting alpha to 1.
So it removes all semi-transparency.
Temporarily, for this part of the loss, yes. Then it renders the object onto a random solid background color like bright blue or green or black. By calculating loss on this hard-rendered output, the VAE is pushed to learn the object's inherent color, ignoring any transparency effects.
But wait, if you make everything opaque, don't you lose the crucial information about, say, the subtle glow on a jellyfish or fine hair strands? That seems risky.
That's exactly why you need both rendering functions. The hard render provides that solid color foundation, but the soft render handles all the nuance.
Okay, so $3.
$3 is basically the standard way you'd render RGBA. It uses the actual alpha values from 0 to 1 with all the gradients. This function is essential because it provides the joint guidance for both the alpha channel and the RGB channel together. It's how the model learns those smooth transitions, the semi-transparent parts like glass or lace.
Got it. So the hard render anchors the color. The soft render handles the combined color and transparency nuances. It's a dual approach.
Precisely. And this feeds into the VAE's final training objective, the loss function Lawler. It's actually quite sophisticated, a composite loss.
Composite meaning it looks at multiple things.
Yes, it gets guidance from 3 different outputs.
Yeah.
The reconstructed alpha video itself, the soft-rendered RGB video, and the hard-rendered RGB video.
Okay, 3 outputs, and then...
For each of those 3 outputs, they apply 3 different types of loss calculation. So it's like a 9-part objective function really working together.
Oh, okay. What are the 3 types of loss?
First, there's the basic reconstruction loss. That uses the L1 norm, just penalizing simple pixel-by-pixel differences between the prediction and the ground truth. Pretty standard stuff.
Okay, the basics. Then what?
Then they bring in perceptual loss, Poon. This is really important for visual quality. It goes beyond just pixel values.
How does it work?
It uses a pre-trained neural network, usually VGG, to extract deeper features from both the predicted video and the real video. Then it calculates the difference between these features. This helps ensure the output looks good aesthetically, not just numerically close.
So it captures more high-level visual similarity. Makes sense.
Right.
And the third loss component.
The third one is crucial for transparency. Edge loss.
Yeah.
Love dollars. If you're doing professional matting, you need sharp, clean edges on your alpha channel.
Right. Blurry edges look terrible.
Exactly. So they use the Sobol operator, which is essentially an edge detection filter, to find the edges in both the predicted alpha and the ground truth alpha. Then they calculate the difference between these edge maps.
Ah, so it directly penalizes the model for generating fuzzy or incorrect boundaries.
Precisely. It's like building a sharpness requirement directly into the training, ensuring those crisp alpha masks that are so important.
Okay, that VAE training process sounds incredibly thorough. Moving on from the VAE, the next stage is training the actual generative model, the part that takes text and makes the video. And here, data quality seems paramount.
Absolutely. Wan-Alpha clearly put a huge emphasis on data curation. You can have the best architecture, but if the training data is poor, the output won't be great.
What did they use?
They combined data from, I think it was 10 image matting datasets and 3 video matting datasets, plus they carefully selected more from the internet. It ended up being around 77,000 high-res training videos.
And they focused on specific qualities.
Yeah, prioritizing high resolution, smooth motion, and a good diversity of content to make the model more general.
And it wasn't just the video data. They were meticulous about the text descriptions, too, the captions.
Very meticulous. They did an initial pass using a powerful vision language model, Qwen 2.5 VL, to generate captions. But then, and this is key, they did manual refinement on every single caption.
Manual refinement. That sounds like a lot of work.
It is, but it pays off. They didn't just fix errors, they added specific labels into the captions. Things like motion speed, visual style, camera shot size, even flags for quality problems in the source video.
So really detailed instructions for the model.
Exactly. That kind of high-fidelity alignment between text and video is vital if you want the final diffusion transformer, to really understand and follow the text prompts accurately.
Okay, so that brings us to that final piece. Training the generative backbone itself. They used a diffusion transformer, a DIT, but with a specific training technique.
Yes, instead of using the standard LoRi low-rank adaptation, they opted for DORA.
Dora. What's that?
It stands for Weight Decomposed Low-Rank Adaptation. It's a slightly different way of adapting the pre-trained model weights. It separates the updates into magnitude and direction components.
Okay. A bit technical, but what was the practical reason? Why Dor instead of the more common LoR?
Well, according to their paper, they found that DOR actually yielded better semantic alignment. The video matched the text prompt more closely and just generally higher overall video quality compared to using standard LoRa for this specific task.
Interesting. So that finer control offered by Dora seemed to be beneficial for this complex RGBA generation.
It seems so. Suggests that for these really nuanced generation tasks, the details of how you adapt the model can make a real difference.
And the underlying mathematical framework for the diffusion training itself, they use something called rectified flow. That sounds deeply mathematical. Why should we, the listener, care about the path being a straight line in the latent space? How does that actually impact the final video?
That's a really good question because the math does translate directly to the quality you see. Think of traditional diffusion, like mapping data to noise along a winding, potentially complex path.
Yeah.
Rectified flow tries to make that path a straight line.
Okay, a straight line path. So
A straighter path means the whole generation process is fundamentally simpler and more stable. From a practical standpoint, this usually means faster sampling. You can generate the video quicker. But critically for video, it helps minimize things like flickering or weird artifacts that can happen when the model jumps awkwardly between steps.
so that mathematical straightness leads to smoother, more stable generation visually.
Exactly. It contributes to a more aesthetically pleasing and coherent final video output. Less random noise, smoother transitions.
Right. And all this careful architecture and training really seems to show in the results. Looking at their examples, Wan-Alpha generates effects that seemed impossible before, like really convincing crystal glasses, pouring liquids, even glowing jellyfish with super fine details in the tentacles.
Yeah, the qualitative results are pretty stunning. The sharpness of the alpha edges and the consistency of motion are noticeably better than what we saw from Transpixeler.
But you mentioned efficiency earlier. That seems like the other massive win here, especially for practical use.
Oh, absolutely. The speed difference is kind of staggering. They report Wan-Alpha is roughly 15 times faster than the open-source version of Transpixeler.
15 times. What does that translate to in real numbers?
Well, they give an example. Generating 81 frames of video at a pretty good resolution, 480 by 832, running at 16 frames per second. Wan-Alpha does that in just 128 seconds.
Wow, just over 2 minutes.
Yeah. Compared to potentially much, much longer for the older methods. If you're a designer or a game developer or a VFX artist needing to churn out lots of assets.
That speed makes a huge difference to workflow.
A massive difference. It cuts down iteration time, reduces compute costs, and just accelerates the whole creative process.
And importantly, they got this speed boost without adding extra complexity when you actually run the model, right? For inference.
Exactly. That's the beauty of using these parameter-efficient tuning methods like LoRa for the VAE bits and DORA for the DIT. All those learned adjustments can be merged directly back into the main model weights before deployment.
So no extra computational overhead at runtime.
Pretty much none. It just runs like the base model, but now with RGBA capability. They even support super fast 4-step inference without needing classifier-free guidance, using another technique called Xiaol.x. Very deployment-friendly.
It sounds almost too good to be true, but the researchers themselves pointed out some limitations, didn't they? What are the remaining challenges?
Yeah, they were upfront about a couple of things. First, sometimes the model might still leave behind bits of unintended background elements, like the masking isn't perfectly clean yet.
Okay, some visual noise occasionally.
Right. And second, relatedly, the generated alpha masks themselves aren't always perfectly accurate. You might see small missing regions or holes inside the object sometimes, especially with very complex shapes or motion.
So still some room for improvement on those really tricky edge cases for the alpha accuracy.
Definitely. Refining that final level of mask precision will likely be the focus for future work building on this.
Okay, so wrapping this up, what's the big takeaway here for you, the listener? I mean, Wan-Alpha seems like a really strong case study.
I think it shows that the path forward for advanced AI generation isn't always just about throwing more data at bigger models. It's about really smart, meticulous architectural design.
Like how they integrated the alpha channel cleanly into the VAE.
Exactly, and using those clever composite loss functions with the hard and soft rendering.
And leveraging efficiency techniques like Dora.
Right. It demonstrates that you can achieve highly specialized, high-quality results and practical efficiency by building intelligently on existing strong foundations, like these diffusion transformers.
And this shift towards parameter-efficient tuning on top of powerful base models feels really important.
It's critical, I think. It lowers the barrier to entry, makes these advanced tools more accessible, more deployable for creative industries, for game development, for anyone who needs this kind of capability. It helps democratize it.
Absolutely. So the paper itself notes how hard it is to represent complex physics like transparency and light refraction in these digital latent spaces. Wan-Alpha's success with things like realistic crystal and liquids is a big step. It makes you wonder, given the success with semi-transparency and fine detail, what other really challenging physical phenomena might these kinds of specialized, efficiency-focused models tackle next? Maybe things like, I don't know, complex atmospheric turbulence, or really chaotic fluid dynamics, or maybe even subtle light effects like subsurface scattering in skin.
That's a fascinating question.
Yeah.
Once you prove you can elegantly handle something as tricky as transparency, it definitely opens the door to modeling other complex dynamic physical properties within these generative frameworks. Turbulence, fluids, light scattering.
Yeah, it'll be exciting to see where they go next.
All right, let's get right into it. We're taking a look at a new research paper that's introducing a model called Wan-Alpha. And its whole goal is to do something that sounds simple, but is actually incredibly difficult for AI. Generate really high-quality videos that are already transparent. Ready to just drag and drop into any project you're working on. This could seriously be a game changer. So here's our roadmap. First, we'll talk about why transparency is such a tough nut to crack for AI in the first place. Then, we'll get into how the researchers solved a huge problem with data. After that, we are going under the hood of the Wan-Alpha method itself. Then, the fun part, the results. And finally, we'll talk about what this all means for creators. Okay, so let's tackle the main challenge here. Why is generating a video with a transparent background such a big deal? Well, it all boils down to one critical piece of information that, honestly, most video formats just don't have. And that missing piece is something called the alpha channel. Now, we're all familiar with RGB, right? Red, green, and blue light mixing together to create all the colors on our screens. RGBA simply adds a fourth channel to the mix, A for alpha. But this channel isn't for color, it's for transparency. It tells every single pixel how see-through it should be. You've definitely seen this checkered pattern before in Photoshop or other editors. That pattern isn't actually part of the cat picture. It's just a visual way of showing us which parts of the image are transparent. So the AI has to do two jobs. It has to generate the cats, and it has to generate a perfect invisible mask that separates them from everything else. Now, trying to do that for a moving video, well, that's where the real problems start. First off, there just isn't a lot of high-quality, transparent video data out there to train an AI on. It's super rare. Second, a model that's great with a single picture can totally fall apart with video. As things move, you get this awful flickering around the edges of the transparent parts. And a lot of the older methods, they basically had to build two AIs that work together, which, you guessed it, doubles the processing time and cost. And that brings us to a really key insight from this paper. You just can't build a great model with bad ingredients. The Wan-Alpha researchers knew this. So their first big innovation wasn't even about the model itself. It was about the data they fed it. They didn't just grab whatever they could find. No, they meticulously combined 13 different data sets. They were super strict about quality control, tossing out anything that wasn't high resolution or had choppy motion. They actually went looking for the hard stuff, things like glass, smoke, and glowing lights, so the model will learn how to handle tricky situations. And get this, they manually rewrote the text descriptions to make sure the AI really understood the connection between a prompt and the final look. Okay, so with this amazing dataset ready to go, the team could finally design the engine to take full advantage of it. And what they came up with is both super clever and really powerful. So the whole system is built around a structure called a VAE, or Variational Autoencoder. Here's how they did it. First, they take the input video and split it in two, one stream for just the colors and another for just the transparency mask. Second, these two streams get processed by standard encoders. Think of these as off-the-shelf AI parts that are already great at understanding images. The key here is that these parts are frozen, which saves a ton of training time. Third, and this is their secret sauce, a custom merge block efficiently combines the information from both streams into one shared understanding. Finally, two decoders use that shared knowledge to rebuild the video, one handling the final colors and the other handling the final transparency, perfectly in sync.
That shared understanding I mentioned lives in something called the latent space. The easiest way to think about it is like a super compressed blueprint. Instead of having one blueprint for the colors and a separate one for the transparency, the AI creates a single, highly efficient blueprint that has all the essential information for both baked right in. It's this unified approach that makes the final result look so good.
And to make sure that blueprint is as accurate as it can be, the model gets graded on multiple things at once. It's kind of like a grading rubric in school. The AI gets a score for how good the colors are, a score for the transparency, and crucially, another score for how clean and sharp the edges are. This forces the model to nail every single detail, not just the easy parts.
Okay, so that's the theory. A better dataset, a smarter architecture. But does all that academic work actually pay off? Let's take a look at what this thing can do. First up, let's look at one of the hardest things for an AI to generate, semi-transparency. We're talking about things like glass or water or smoke. And wow, this example just says it all. On the left, you see a generated crystal flower. On the right is its alpha channel. Now notice, it's not just black and white. You see all those shades of gray? Those perfectly map to the different levels of transparency in the crystal. This kind of nuance is exactly where older models would have failed.
All right, next up is another effect that often trips up AI models, soft glows and complex lighting.
Take a look at this street lamp. The model doesn't just create the lamp itself, it creates that beautiful soft glow of light around it. In the alpha channel, this shows up as a smooth gradient, which means you can place this object into any new scene and it will look like it's actually emitting light. It's incredible.
But what is maybe the most impressive test of all is how it handles things with tons of tiny, fine details.
And here it is. This is where Wan-Alpha is just on another level. Fur and hair are famously, notoriously difficult to cut out cleanly. Even for a human artist with a ton of time, it's a huge pain. But this model generates both the cat and a pixel-perfect alpha channel that captures every single one of those tiny, wispy strands of fur. This is just a massive leap forward in realism.
So the quality is obviously top-notch. It's state-of-the-art. But for any tool to be really useful for creators, it has to be more than just good. It also has to be practical. It has to be fast. And believe it or not, Wan-Alpha delivers here too. How fast are we talking? Just 4 sampling steps. That's it. Because the architecture is so efficient, it can generate a high-quality, transparent video in a tiny fraction of the time other models take. This isn't some research project that runs overnight on a supercomputer. This is fast enough to be built right into the software you and I use every day. So let's just quickly recap the big breakthroughs here. First, Wan-Alpha gives us superior quality, absolutely nailing difficult things like transparency, glows, and fine details. Second, its design is incredibly smart and efficient, adding no extra computational cost. Third, that efficiency makes it truly practical for real-world use. And finally, it's a powerful reminder that in the world of AI, everything starts with good data. Garbage in, garbage out is truer than ever. And that really brings us to the big question. For decades, creating professional video assets for games or for films, or even just for social media, has been this slow, expensive, and difficult process. Now, an AI can generate them from a simple text prompt in just a few seconds. So, what new kinds of art, what new forms of creativity does this unlock? What will you make next?